Momentum is a systems parameter. So in general, when people talk about the word momentum, a lot of times they focus on one thing, one object, like the momentum of a car or the momentum of a baseball. It's more complicated than that. It turns out that momentum is really about the center of mass of a system. So it's a systemic property, not an individual property. And so what we did here is that we started with Newton's second law. And what we said with Newton's second law is that the way Newton wrote down Newton's second law for the first time, it says that the rate of change of momentum is equal to the net force. In other words, that the net force was equal to this rate of change of momentum, where P is a vector, is mass times velocity. And this is what we define as momentum. And I'll just leave it there for right now, but that is the definition. And so when I look at the unit of momentum, a unit of momentum is a unit of mass times velocity. And the most common unit that people use is they use a Newton second. And that's the one that I will do here. So then what we did here is that we then defined momentum. So the definition of momentum is this. It says here that the momentum of an object, and the key thing here is that look what it says. It says change. It doesn't say P, it says change in momentum. Now, it turns out that when you look at this force, a net force, we always assume that this thing was a constant. Interaction forces are not a constant, but a function of time. And it turns out that this is equal to something called the impulse. And the impulse is essentially Newton's second law rewritten. And we typically write the impulse as J of t, and it is technically the area of force of time versus t curve. This is the definition of momentum. So now you can see how I would tell my kids here, it goes like, they said the word momentum, I go like, what the hell does that mean? Not very many people are going to make this statement. So momentum is quite a different parameter. And we said a couple of things here. Okay, so if I now start to, again, this is just a review because we're online. Versus face-to-face. And I think that since many people are not going to be here, I just want to make sure that I try to do the best of getting my point across here, is that only changes in momentum are meaningful. Look at the definition of momentum, right? Look at the definition of momentum. So when I look at that word meaningful, that is a green light telling me that I can only talk about changes. And what that really tells me here is that we need a reference point to compare momentum to. So if you don't have a reference point for momentum, it's meaningless. So then I could come over here and just say that momentum by itself, that is, if you see somebody write momentum P just like that, this is meaningless. And that's a really hard thing to kind of grasp, because up to this point, we really have not had to do. It's because we didn't have to do that. That really didn't, it's never really done that. So the answer is, I just saw that there's a chat here. The will be recorded and posted on Canvas and up to YouTube. Yeah, it's the same as before. No difference here. Okay, so then another thing that I think important to review here is that this term up here, this is called the impulse momentum theorem. And so then I could say here is that the impulse momentum theorem is applied to different ways. So when you look at the way I have a tendency to write it here, is that I write the change in momentum. So physically, it reads best if you write it like this: P2 minus P1, and this is going to equal to the impulse, which is a function of time. So in other words, I have P2 is equal to P1 plus J. Now, these are all vectors here. And so what you're seeing here is that when we talk about the impulse, what we do here is that we focus on one type of impulse. It's called the external impulse. And so here's what we say here. If the external impulse is not equal to 0, then momentum changes. If the external impulse is 0, then what we say here is that momentum is a constant of the system. And it turns out that's the whole chapter right there. We're going to start off with the impulse not equal to 0, and we're going to show that this is really if we have an object acting external on a system. As then the second half of the chapter, we now look at as a system viewpoint, and therefore all impulses are internal, and as a consequence, the momentum is 0. Uh-oh, somebody just rang the doorbell, so the dogs are going to bark. Yep. Sorry about that. So when I write the impulse momentum theorem, it's J as a function of time. Okay, this is not J times T, it's J because the impulse is a function of time. And I'll look at that very briefly here. So then again, just continuing the review, here's what I find here. Then we ask the question, what is an impulse? And the image that I gave you here is that when we talk about momentum, we always want to talk about collisions. So momentum is about collisions. On the other hand, energy is not about collisions, but momentum is about collisions. And so when you see this, here's what we're looking at. And this is an image that I showed you in lecture already, but I think it's a very important thing here. And what you're finding here is that you're seeing that a baseball is going this way, and then it starts to slow down. And then right here, it reaches a speed of 0. It starts to speed up again, and it gets faster and faster. So if I start to look at these frames, 1, 2, 3, 4, and 5, in these 5 frames, what you're seeing here, that the applied force by the bat on the ball is time dependent. Okay, it's time dependent. So when I look at the impulse during a collision, this thing is a function of time. And if you've had calculus, that's the integral of force dt here. And so this, by definition, is the area. Okay, so this is how we have to find impulse. Okay, so now, what does this mean here? Here, hold on a second here. Are you guys hearing me okay? I think you should be able to hear me. Okay, so now when I look at this thing, here's what we see about this collision. If I look at the ball collision, what we said here is that because it's time dependent, what I see here is that I have a plot. And what I'm seeing here is that I'm seeing a curve that looks something like this. And then I imagine that it turns out symmetrically like this here. And what do I mean by the symmetricness of this thing? Well, first here, this beginning part here, this tells me about frames 1, 2, and headed towards 3. So this becomes the compression. And then as I go from frame 3, 4, and 5, this now becomes the expansion of the ball. And so what we define as the impulse is the area under this curve. So when I look at that area, this is by definition the impulse, where the time, what we call the contact time, which is this delta t here, as it goes from here to here, we're seeing here is that this guy right here, this is where contact begins. And then right here, this is where contact ends. And what we're seeing here is that we can talk about a couple of points here, that this represents the maximum force. That's what the impulse is. But one of the things that we said here before is that we can use this thing called the mean value theorem of calculus. And it says that we can, as long as these two areas are the same. Okay, so in this case, if I come in here and I pick an area, that's equivalent. So if I look at this area, and all I'm trying to do here is that if I still make this my contact time, so from here to here, I still have the same contact time during the collision. And if this area, the blue area, is equal to the red area, then we can define this point here as an average, a time averaged force. And so the beauty of this is that we could go in and we can define this, where we could then say that if I look at the impulse, then I could then say that the impulse, which is equal to the area, I can also write this as the timed average force times the contact time. And this right here is conceptually very powerful.